Hi, chemistry students, and welcome to class number 2 in week 12. Today, we are going to talk about a new topic about radiation and the learning goals for today. We are going to list the different types of radiation and provide examples of each. We are going to use the energy spectrum to determine high and low frequency radiations. We are going to types of nuclear radiation, and we want to compare between the chemical processes against the nuclear processes. In general, we have two types of radiation. We have electromagnetic radiation, which arise due to the interaction between electrical and magnetic fields around us. And the other type, it is radiation, which arise due to the unstable nucleus of atoms. We want to discuss the energy spectrum. And the energy spectrum refers to the many types of radiations which are released from the sun. And this energy travels in the way of waves. We have something called frequency of the wave. The frequency describes how many waves are produced per second. And when we check, or the scientists describe the energy spectrum in a long line. In this spectrum, we will notice that we have two types of radiation: the non-ionizing radiation and the ionizing radiation. What is the difference between them? Listen to me carefully. For the non-ionizing radiation, we will see that the waves have a long wave frequency or long wavelength. Can you see how the waves are moving? They have long wavelength and they have low energy and they have low frequency. So we say that for the non-ionizing radiation, they have long wavelength, they have low frequency, and they have low energy. That's why we say that the non-ionizing radiation, they don't carry enough energy to ionize the atoms. So these radiations, they don't have enough energy to ionize the atoms. While on the other side, we have called ionizing radiation. The ionizing radiation, they are characterized by short wavelength, they have high frequency. Can you see that how the numbers of waves are more per second? And that's why they have high energy. What is the meaning of they have high energy? That means they have the energy, high energy. That means that when they strike a molecule in the path, they can remove the electrons and ionize the atoms. And so they are very dangerous. Like if a human beings or the cells exposed to such kinds of radiation, this radiation has the ability to penetrate the cells and damage the DNA. And this is some kinds of applications like in our life for the non-ionizing radiations, and even the visible light, like this is the radio frequency radiations, the visible light, and all of that are non-ionizing radiation. While ionizing radiation like the X-rays, the gamma rays, the cosmic rays, and they are, as we said, that they are very dangerous. So which radiations are dangerous and which radiations are harmless? So as we said that the low frequency radiation or non-ionizing radiations, they are harmless. But in one condition, if the exposure of this radiation is short term. Examples like the radio wave, microwave, visible light. While the high frequency or ionizing radiations, they are harmful. Like the X-ray, the gamma rays, the ultraviolet ray, the alpha particles, beta particles. So this is very important points when we compare between the low frequency or non-ionizing radiations and the ionizing radiations. The high frequency or ionizing radiations are more harmful than the low frequency radiation. But the long-term exposure to any type of electromagnetic radiations can cause harmful to the human body. What is some effects of long-term exposure to non-ionizing? So by exposure for a long time to non-ionizing radiation, we can have some problems. But like if we are exposed to the cell phones, the Wi-Fi, the microwaves, that will increase the risk of some disease like the leukemia, brain tumors, breast cancer, Alzheimer's disease, reduce melatonin levels, changes in brain function, nervous system, and immunity. How we are going to prevent ourselves? The step, we have to make a space to put a shield, keeping the cell phones at a distance from head, body, and out of bedroom, turning home routes, and spending time in nature, of course, are extremely helpful. And this is in this slide, we give you some advices to reduce the dangers of radiation. Avoid carrying the cell phones in pockets, because to be avoided from your heart and your internal organs. Avoid using laptop in your lap when it is connected to the power source. Use a speakerphone instead of the Bluetooth. Keep the bedroom clear of as many electromagnetic devices. Try to avoid halogens and fluorescent light. Avoid Wi-Fi or unplug it when not in use. Let's revisit the difference or the meaning of isotopes. We talked about the isotopes, I think, in week 4, and we said that the isotopes are the atoms of the same element which have same atomic number or number of protons, but they have different mass number. What is the mass number? It is the number of protons and neutrons. For example, if we have the sodium has 2 isotopes, sodium 23 and sodium 24. What is the difference between them? Both of them have the same atomic number, but the mass number is different because they have different number of neutrons. In these isotopes, we have 12 neutrons in the nucleus, while here we have 13 neutrons in the nucleus. Isotopes and nuclear radiation. The nucleus of any atom, maybe it will be stable or unstable. We are going to talk about the unstable nucleus. When we have unstable nucleus, it will be spontaneously decomposed by emitting either particles or energy to change its state from unstable to that's we call it radioactive isotope. So the radioactive isotope is the isotope of an element that emits radiation. So we have isotope, and this isotope has a nucleus, and the nucleus is unstable, and it will emit particles or radiation or both of them, that we call them, this isotope, we are going to call it radioisotope. We have types of nuclear radiation that we are going to talk about them now. We have something called alpha particles, and the alpha particles is given this symbol alpha 24, or it has the nucleus of helium atom 24. The beta particles, which will take the symbol of electron -1, negative electrons, or we give it the symbol of beta -1, 0. Positron, which is the symbol of electron positive, or we can give it this symbol. The proton, which has, we can write it the symbol of B11, or hydrogen atom 11. Neutron, which is will giving the symbol of N01. Gamma rays, and this is the symbol of gamma. Let's talk about them in details. The radioactive isotope. We said that when we have a nucleus of radioactive isotope, this nucleus may emit particles, so it will be changed to a more stable nucleus, and that for another element. For example, we have the plutonium, which is unstable isotope. It is 94. This is the atomic number, and this is the mass number. It will emit these particles. These particles is alpha particles. It consists of 2 protons and 2 neutrons. So now the atomic number will be changed from 94 to be 92 because it lost 2 protons. While now it has lost, or it had emitted 4 particles. So the mass number of this nucleus becomes 237. And this is the another, or the nucleus of another element, which is the uranium. So the plutonium, which is unstable or radioactive isotope, will emit particles to change to be uranium. Or maybe isotope, there will not change in the number of the protons or the number of the mass number. That change, there is no change in the atomic number or mass number. So this nucleus or radioactive, the nucleus of this radioactive isotope will emit energy. So it will give more stable nucleus for the same element. So the nuclear radiation may take the form of alpha particles, beta particles, something is called positron, which is beta plus particles, pure energy such as gamma rays. So we have the parent isotope. It will be changed to radioactive decay. Then it will start to emit particles to give more stable isotope and release energy. The alpha particles has protons, so we represent it by H alpha, like symbol of alpha 2, 4. So alpha particles has 2 protons, 2 neutrons. So it has 2 protons, and the mass number is 4. So that means that it has 2 protons and 2 neutrons. This is the mass number. And it is identical to the nucleus of helium. That's why we can represent it like helium 2, 4. The second types of particles, it is the beta particles, which is, we can represent it by B. The beta particles, it is high energy electron, negative electron. with a charge of -1 formed when a neutron is changed to a proton. So can we see this example? If we have, for example, in the nucleus, we have 5 neutrons and we have 2 protons, and one of the neutrons have been changed to a proton. This change will release of or emit the beta particles in the form of electron with negative charge. So we have one neutron had been changed to one proton. One neutron had been changed to one proton that will release or emit the beta electrons. And the beta electrons is by electron with negative charge. And it is high speed electron. While the positron, which is we are going to represent it by B plus 1, is positive electron. And that's produced when a proton, one proton, is transformed to one neutron. So when a proton transformed to one neutron, that will emit the positron, and it is a very high energy, but represent like an electron with a positive charge. The last one is the gamma rays, which is we are going to represent it by this symbol. And the gamma rays are very high energy radiation released from the nucleus when it decays, but there was no change in the mass will happen. So no mass or charge. So the gamma rays doesn't have any mass or any charge. That's why we're represented by 0. So again, let's study this table again. The first type of particles, we have alpha particles. The alpha particles describe high energy helium nuclei consisting of 2 protons, that's 1 and 2, and 2 neutrons. How we are going to represent or make the symbols, we can make it like alpha 2,4 or helium 2,4. Beta particles, which high energy electrons, and they are represented by electron with negatively charged -1, and of course the mass number of the electron will be 0. So we can say that it is E -1 0 or beta -1 0. The positron, it is particles with the same mass as an electron but with 1 unit of positive charge. That's why we are going to represent the positron as E electron, but it has the charge of +1. The proton, which we know it, of course, we talked about before, it is proton 1 1, it is the nuclei of hydrogen atom. The neutron, which is N01, it is particles with a mass approximately equal to that of a proton, but with no charge. So the difference between the neutron and the proton, that the proton has a positive charge, while the neutron, there is no charge. The gamma rays, that's energy. It's very, very high energy electromagnetic radiation. So that's why we write 0 here and we write 0 here. So there is no charge or no change in the mass. Let's compare between chemical processes against nuclear processes. Chemical reactions involve changes in the electronic structure of the atom. So the atoms will gain or lose or share electrons. But there is no change in the structure of the nucleus. The nucleus contains protons and neutrons. In this topic, or in this case about the nuclear reactions, the nuclear reactions are concerned about the changes takes place inside the nucleus. So when the number of protons in the nucleus change, the atoms become a more or becomes a different element. Thank you very much, and we are going to meet tomorrow in our class.